First steps. So this is a sub k. Compute the limits of a sub k. Well, you can see this is minus 1 ln of k plus 1 to the k. Sorry, it's everything to the k. Okay, so this is a exponential function. So you can see when k goes to infinity, the denominator inside is going to be bigger, bigger, bigger. So this function is going to be smaller, smaller, smaller. So as long as the base is less than 1, then our our exponential functions looks like that. Okay, it's decreasing. So when x goes to infinity, the answer is 0. Okay. So that's why here we can divergence test is inconclusive. So we go to the second step, because all the terms to the power of k, we use root test. Okay. So root test q is limits k goes to infinity and the k roots of a sub k. So here limits k goes to infinity, k root of a sub k. So absolute value of a sub k, we actually get 1 over ln of k plus 1, and then to the power of k. So this k's cancel. So that's why here we get the limit k goes infinity of 1 over ln of k plus 1. And when the denominator goes to infinity, the answer is 0, because 0 is less than 1. Okay, so by the root test, series converges. Okay, so here I want to emphasize. So sometimes students get confused about limits of a sub k and the q, and sometimes they get, let's say they get a q is like 1/2, they say, this is not 0, so divergence by divergence test. No, divergence test, we are looking at the limits of the sequence a sub k, where the root test, we look at the k root of the sequence. Okay, and if the q is greater than 1, we have diverges, series diverges. If q less than 1, the series converges. Okay, but for the divergence test, as long as it's not 0, then diverges. Okay, so try to compare them and not confuse with the different numbers. Okay, part C. So let's continue. Let me get the black color. So first step. So this guy is a sub k. So a sub k is limits k goes to infinity 1 plus 1 over k to the k squared. Well, you can see here when k goes to infinity, the inside goes to 1, and this guy goes to infinity. So 1 to the infinity actually is indeterminate form. Okay, but to calculate this limit is actually more difficult than calculating the limits of the root test. So that's why let's skip to the next steps. Let's look at the root test. So q is the limit k goes to infinity of the k root of absolute value of a sub k. So we have limits k goes to infinity. So the k a sub k. Well, what does the k root do? The k root actually simplify the limits a little bit. Now we just have to the k. Well, do you remember what this is? We just did this in example. Let's see. In our previous example here, So we just did it here, and the answer is E. Okay, so the answer is E, and because E is greater than 1, so we get the series diverges. Okay, so that is the example 2, part C. All right, let's look at the... So next is gonna be, let's go back and look at comparison test and the limits comparison test. We talk about ratio test and root test. Now let's look at the two different kinds of comparison test. Okay, so comparison test. Let me change the color. Okay, so suppose we have the series A sub k. So this is what we are looking for. Okay, so this is the unknown series. Okay, suppose we have another series that is known. Okay, with positive terms, and let's say oh, let me see. Okay, let me see. Oh, so this is a little bit different, okay? So suppose AK and series AK and series BK are series with positive terms, and we have the BK is the big guy, and AK is the small guy, okay? And then we know if big guy converge, then small guy converge. If small guy diverge, then the big guy diverge. So this is very similar to what we did for the integral, right? The comparison test for the improper integral. So if big guy is finite, then the small guy is finite. If small guy is infinite, then the big guy is infinite. Okay, so right now we just replace integral by the sum. Okay, so they work the same. So that our unknown series could be the big guy or could be the small guy. Okay, let's look at the limits comparison test. So the limit comparison test, suppose A, K, and BK are series with positive terms. So here, this series is the unknown, so it's the series we're looking for. And BK is some known series, okay? And usually it's the K series, okay? Because we know the K series by the integral test, we know the K series, okay, from 1 to infinity. Okay, K to the P. This guy, okay, converges if P is greater than 1. And it diverges if P is less than equal to 1. Okay, so that's why we know this series. All right. Okay, so we compute the limits of A sub k over B sub k. Okay, if this limit equals L, okay, so let's look at the three cases. If L is a number that is greater than 0, but less than infinity, okay, then both series either both converge or both diverge. Okay, so if the limit is a number, okay, not 0 and it's a finite number, then both series either they both converge or both diverge. Okay, if L is 0, L is 0 means which one is bigger? The numerator is bigger or the denominator is bigger? Well, it's 0, it means the denominator is bigger. So that's why if the big guy, so this is bigger, right? So if big guy converge, then the small guy also converge. Okay, so if the limit is 0, this is the big guy and this is the small guy. So big guy converge implies small guy converge. If L is infinity, if this is infinity, which one is bigger? The numerator is bigger, right? So that's why if the small guy diverge, then the big guy also diverge. Okay, so that is the comparison test and the limit comparison test. So usually I suggest you to use the limit comparison test. Okay? And we will see why. Okay, so example 3. Use comparison test and limit comparison test to determine whether the following series converges. Okay, let me use, how about let me use orange color for comparison test and use green color for limit comparison test. Okay, so comparison test, you want to compare it with some series, okay? We know, okay, but we don't know which one is the big guy, which one is the small guy. So usually you can see here when k goes to infinity, the dominant terms dominance. So we compare with the dominant terms. So what is the dominant terms? Well, the dominant terms is like 4k squared over square roots of 7k to the 9, right? That's the dominant term. So that is 4k squared. And then we have square root of 7, split them. And then we have k to the 9 over 2. So we group the coefficient together. And then, okay, let's see. K squared and k to the 9 half. K to the 9 half is bigger. This is bigger, right? So once we cancel this k squared, we have the k in the denominator. And 9 half minus 2 is what? That is 9 minus 4, which is 5. 5 half. Okay, so this is 5 half. So this is a series we want to compare with. Okay. By the way, you can see if you do the first step, you do the first step. Okay, you do the first step. The limit k goes infinity of a sub k, because we look at the dominant term. So that will be equals to, so these are the dominant term. Okay, so 4 over square root of 7. And then k to the 5 over 2. You can see the denominator goes to infinity while the numerator is constant. So this is 0. So we get the divergence test is inconclusive. So we go to step 2. So step 2 is either comparison test or you can use limit comparison test. Okay, now let's see the difference. Okay, so next. So comparison test. Okay, so we want to compare our function with this guy, right? We already know. So that is 4k squared, 7k to the 9. Okay, which one is bigger? Well, you look at the difference. The numerator are the same, so the difference is the denominator, are the denominators. Okay, so we look at the denominators. Can you tell which one is bigger? Oops, I just realized I have a mistake. This is not x, this is k. So typo. Okay, which one is bigger? Well, the left, right? Because you have more terms, 2k plus 1, k is positive. And then, so from here, what is this guy? Okay, the number with a bigger denominator will be actually smaller. So this is the big guy. This is the small guy. Okay, now what's the series of the big guy? So the series of the big guy is k from 1 to infinity. We know our big guy is the same as 4 over square root of 7, 1 over k to the 5 half. So this series, 4 over square root of 7, 1 over k to the 5 half. This is a p series where my p is 5 half. So p is 5 half is greater than 1. Then the series, what? The series will actually converges. Okay, now we have the big guy converges. What can you say about the small guy? So by comparison test, the small guy, which is our series. If you don't want to copy the whole series, you can call, at the beginning, you can call this guy is a sub k. Then we say a sub k also converges. Okay. Oh, and the previous steps, you can say this series converges by the p test, because we look at the p. If p greater than 1, we have converges. If p less than or equal to 1, we have diverges. That is the p test. Okay, so that is the comparison test. How about the limits comparison test? Okay, so the limit comparison test, or what you do is you compute the L. The L is actually the ratio between those two series, okay? So that's why it equals to our a sub k is 4 to the k squared over 7k to the 9 plus 2k plus 1 and over b sub k. So what do we want to compare with? This is b sub k. So 4 over square root of 7, 1 over k to the 5/2. And what is the limit? And remember, because when k goes infinity, how do we get this? How do we get this guy? Is by looking at the dominant term of the numerator and the dominant term of the denominator. So actually, they behave the same when k goes to infinity. So that's why L is 1. Okay, so if the way you get the bk is by looking at the dominant term of the numerator over the dominant term of the denominator, then your limit will always be equal to 1. Okay, so and then you say by p series, we know that our k from 1 to infinity of 4 square root of 7, 1 over k to the 5/2. We know this series converges because p is greater than 1. Then we can say by limits comparison test, our original series also converges. Okay, so here there's some parts I want to emphasize because you can see the comparison test and the limit comparison test, there are two series involved. So in the previous examples, you see sometimes we answer a problem like series converges, but here you cannot just say series converges. Which series do you mean? Okay, so you have to tell me this series converges and this series converges. You have to tell me which series you mean. Okay, so you have to tell me, and you cannot just say series converges. Which series do you mean? Okay, so that is part A. How about part B? All right. Okay, so part B, I would say the first step still the same, and this is a sub k. Okay, so the first step, we compute the limit k goes to infinity of a sub k. Well, what do? You look at the dominant term of the numerator, which is 4k squared, and the dominant term of the denominator, which is 7k to the 9. Well, actually, this is the same as what we had before, right? And so we have 4 over square root of 7, and this is 1 over k to the 5/2. Okay, so this example is very similar to what we had before, but you can see the denominator is a little bit different. And when k goes to infinity, we also get 0. Okay, so now let's use comparison test. Okay, so we have 4k squared over 7k to the 9 minus 2k minus 1. All right. We want to compare with 4 square root of 7, 1 over k to the 5/2. Okay, so which one is bigger? Well, we know this is the same as 4k squared over square root of 7k to the 9. Okay, so the only difference are the denominators. So let's look at the denominator. Which one is bigger? So which one's bigger? Well, this is subtract some number, so this is bigger. Then the number, if the denominator is bigger, the number is smaller. So we have this. Okay. All right. So that's why we get this is the small guy and this is the big guy. And we can remember that k from 2 to infinity, 4 over square root of 7, 1 over k to the 5/2. This guy, the p is greater than 1, so this guy converges by the p test. But if you get the small guy converges, can you talk about the big guy? If small guy converges, can you talk about the big guy? No, we have no conclusion. The big guy can converge or diverge. We have no conclusion. So actually the comparison test here, we fail. Okay? Yeah, so that's the limitation of the comparison test. You have to only one way works, like the big guy converged, then small guy converged, and the other way, small guy diverged, then the big guy diverged. If the big guy diverged, we have no conclusion about the small guy. If the small guy converged, we have no conclusion about the big guy. Okay, so those are the limitations of the comparison test. Well, let's look at the limits comparison test. You can see L is the limits k goes to infinity, a sub k over b sub k. So here, a sub k is 4k squared, 7k to the 9 minus 2k minus 1, and b sub k is 4 over square root of 7, 1 over k to the 5/2. You can see here, when k goes to infinity, we only just need to look at the dominant term. So the dominant terms are this, and this, right? And because how do we get b sub k? We look at the dominant term of the numerator and denominators of a sub k to get those. So this answer is still 1. So as long as it's a number that is finite number, which is not 0, then we have both series, either both converge or both diverge. So that's why the series 4 over square root of 7k to the 5/2. Okay, this guy converges by the p test. Then our series, so by comparison, by limits comparison test, our series also converges. So limits comparison test work here. So limit comparison test, we actually just look at how the series behave at the end. We don't really care like which one is bigger, which one is smaller, as long as they behave like the same approximately. Okay, then those two series, they both converge or both diverge. Okay, so that's why I strongly recommend you to do limits comparison test, because it works more general. Okay, so it works. Okay, so let's look at example 4. So from now on, we just use limit comparison test. Okay. First step, that is our a sub k. So first step is, I'm afraid I don't have enough space. Okay, so first step is compute the limits of the sequence. So we look at the dominant terms, okay? So what's the dominant term of the numerator? The dominant term of numerator is actually cube root of 8k squared. What's cube root of 8? 2, and then we have k squared and cube roots. Okay? And the dominant term of the denominator is cube root of k to the 4th. So don't forget the cube roots. So that is k to the 4/3. Alright, so we have 2k to the 2/3 over k to the 4/3. So the denominator has more k. So we have k to the 4/3 minus 2/3 is 2/3. Okay, so when k goes to infinity, this guy is 0 because our denominator goes to infinity. Okay, so the second step, and we also know that this is the series we want to compare with. So L is the limit. K goes to infinity, a sub k over our series 2, and then k to the 2/3. And then we know the answer is 1. Because how do we get this series is by looking at the dominant term of the numerator and dominant term of the denominator of a sub k. So that's why we know the limit is 1, okay? Because the limit is 1, they either both converges or both diverges, okay? And then by p test, our series k from 1 to infinity, 2 over k to the 2/3. So p is 2/3. 2/3 less than 1, so we know this guy actually diverges, okay? Then by limits comparison test, our series also diverges. Okay, and that's it for part B. Let's continue. Oh, I think this should be part A. Okay, and this is part B. So this is A, and that's B. Okay, so please pause here and try to work on this problem first. After you're done, you can continue to play the video and check our answers. So first, this is a sub k, and the first step is we compute a sub k. What is the dominant term of the numerator? 15k squared. How about the dominant term of denominator? Okay, we have cube root of 2k times square root of 4k to the 5th. So those are the dominant terms. So let's group the coefficient together. So this is like cube root of 2, and then this is like k to the 1/3. Square root of 4 is 2, right? And then we have 5 to the, k to the 5/2. We can combine the two together. So this is like 2 to the 1/3. 2 to the 1/3 times 2, we can actually combine them. It's 2 to the 4/3. And then we have k to the 1/3 minus, plus 5/2. This is how we combine them. Okay. Let's see, so we have 15k squared, and then here we have 2 to the 4/3, k to the 1/3 plus 5/2. Okay, so what is that? Well, that's 15 over 2 to the 4/3. And then here, the denominator is bigger, you see? So actually, what happened with the 2? The 2, we actually can subtract the 2 here. So, 5/2 minus 2 is 1/2. So it becomes 1/3 plus 1/2. So that's why I didn't add them. I want to simplify more, so then I can add it now. So 1/3 plus 1/2 is actually 2 6 plus 3 6. That's 5 6. So this guy equals to limit k goes to infinity 15 over 2 to the 4/3. And then we have k to the 5 6. And when k goes to infinity, this guy goes to 0. Okay, this limit goes to 0. So that's why divergence test doesn't work. So we go to the second step. We use the limit comparison test. And L is the limit. K goes to infinity. A sub k over our b sub k. What is our b sub k? So this is our b sub k. So that's 15 over 2 to the 4/3, k to the 5 6. And we know it's 1 because how do we get the p series is by looking at the dominant term of the numerators and denominators of a sub k. So they behave the same, very similarly at the end, at the tail, when k goes to infinity. So now we can say by p test, our p series this is, so you can see the p is 5 6, which is less than 1, so this guy diverges. Okay, so we can say by limit comparison test, our series a sub k also diverges. Okay, do you have the same answer? All right, let's continue. So let's look at this problem. First step, this is a sub k. What is the limit of the sequence? Well, that is 1 over k, 1 plus 1 over k. So when k goes to infinity, well, this 1 over k, let me use different color. This 1 over k goes to 0. So this looks like 1 over k to the 1 plus 0 is 1. So this looks like 1 over k. So that's why the limits is 0. Okay, so divergence test doesn't work. So we go to the second step. Use the limit comparison test. Okay, so what do we want to compare with? We want to compare with the 1 over k, right? This is what it behaves like. But so a over b over c over d is a over b. So the k to the 1 plus 1 over k is actually here. And then 1 stay here, downstairs, the k actually stay upstairs. Okay, so what is this guy? This is k and k to the, so you can split. It's k and k to the 1 over k. So they cancel. You get the limit. K goes to infinity of, we can move on the top, that it becomes minus 1 over k. Alright, so now you can see when k goes to infinity, what happens? When k goes to infinity, our k goes to infinity, but 1 over k goes to 0. So this is infinity to the 0. This is indeterminate form. Okay, so for indeterminate form of the type 1 to the infinity, infinity to the 0, 0 to the 0. So all of this indeterminate form, you apply ln to it. Okay, so we continue. We consider the limits. K goes to infinity, ln of k to the minus 1 over k. And then because of the natural log, we can bring the power down in front. So we get limits k goes to infinity minus 1 over k, ln of k. See, it's actually a quotient. Okay, so it's actually a quotient. So a quotient, now when k goes to infinity, we get infinity over infinity, so you can use L'Hopital's rule. So that's why here we get the derivative of ln of k, which is 1 over k. Derivative of k is 1. So that's why when k goes to infinity, this guy is 0. So that's why our L is limit k goes to infinity e to the ln of k to the minus 1 over k. And we just calculate the ln of k to the minus 1 over k is 0. So e to the 0 is 1. Okay, if L is 1, what do we say? As long as it's a finite number, not 0, then the both series, two series, either both converge or both diverge. Okay, so we say by P test. Okay, let's look at our P series. Our P series 1 over k. So our P series actually diverges. And then by the limit comparison test, our series also diverges. So far so good, everybody? Okay, I want to talk about some parts you gotta be very, very careful. So some students they get confused, and sometimes they get here a number. Let's say if they get a 2, they'll say, oh, because it's greater than 1, series diverges. If they get this number is like 0.5, they'll say, oh, less than 1, the series converges. No, so don't get confused with the criterions among different tests. So retest and ratio test, we compare the limits with 1. If it's greater than 1, we have series diverges. If the limit is less than 1, we have the series converges. But for other tests like divergence tests, we want to compare the limits with 0. If it's not 0, diverges. If it's 0, inconclusive, go to the next step. For limits comparison test, we just care about whether this guy is it 0, is it infinity, or is it a number? A number, finite number, it could be any number, it could be 1, 2, 3, 4, 5, 6, 1,000, 1 million. As long as a finite number, then both series, they either both converge or both diverge. Okay? Alright, so part D. Part D, this is actually quite interesting. Okay, you see why. First of all, we compute the limit of the sequence. Okay, we compute the limit of the sequence, and we have the sequence. The numerator is ln of k, the denominator is k squared. So which one is bigger? The k squared is bigger, so the denominator is bigger. So then we have the denominator bigger, the limit is 0. Okay, that's the first step. And second step, well, when you look at this function, this series, you may see, so if you see ln of k over k, you can think about, oh, this is like ln of k times 1 over k. 1 over k is the derivative of ln of k, so you can use integral test. But here, actually, you cannot use integral test because it's k squared downstairs. It's not like k downstairs. So for this guy, you can use integral test. Or if you see this guy, you can also use integral test. You have to see like some factor is the derivative of some other factor, then we can know we can solve the integral by u substitution. So in this problem, we cannot use integral test. Okay, so let's try to use limit comparison test. Okay, so let's see. How about orange? Okay. So this problem is actually quite interesting. You see. Okay. All right. So First, okay, so first, what do we want to compare this series to? Okay, what do you want to compare this series to? Well, what is, we know the denominator is like a k square, right? So it's like similar to a k series, and but the numerator is not like a constant. Okay, so if this is a polynomial, rational functions, we just look at the dominant terms. But this guy, we have ln of k over k squared, but still maybe we can try to figure that out. So what is ln of k? Well, ln of k is what? Is greater than, so when k start from 1, ln of k is actually an increasing function, right? So here, the series converges or diverges. What it really matters is the tail. Okay, so I would say ln of k will be greater than 1 for k large, and ln of k it grows slower than k. Do you agree? So this is for the k large. We know ln of k is going to be greater than 1 and less than k for k large. Okay, so let's look at this guy. So now we have ln of k over k squared. So then we divide by k squared on each of the terms. So you can see ln of k over k squared is actually bounded by two p series, this guy and this guy. Okay, so let's compare them. So first, let's compare with 1 over k squared. Okay, and let's see, what's L? So L is our series over the series we want to compare with. And k squared cancel. So we have the ln of k. Well, that is infinity. What does that mean? So if this is infinity, it means the numerator is a big guy and the denominator is a small guy. Okay, so 1 over k squared, k from 1 to infinity, by the p test. We know this guy converges. See if the small guy converges. Can you talk about the big guy? No. So it fell. And this if we compare with 1 over k squared, we fail. Okay, how about I compare with this? Okay, second, let's compare with 1 over k. Well, then L is limit k goes to infinity, our series ln of k, and then k squared 1 over k. What is that? Well, you cancel one copy of the k, you get ln of k over k. Well, we know that k goes to infinity faster, so the denominator goes faster. The answer is 0. Okay, is 0, what does that mean? I want to emphasize. Okay, so it means denominator is the big guy. Numerator is the small guy. Okay, so let's continue. Okay. Okay, so let's continue. Okay, so now we have by the p series, by the p test, our p series k from 1 to infinity. This guy, oops, this p series diverges. Okay, then Well, what can we say? If the big guy diverges, can we talk about the small guy? No! Oops! So that's why you see I drew 3 lines. So both of them don't work. Okay, so we need to try what color do you like? How about blue? Okay, so 1 over k doesn't work. 1 over k squared doesn't work. So let's try somewhere between. Okay, so let's compare with somewhere between. How about k to the 1.5? Okay, then L is our series over the series we want to compare with. What does that mean? It means k squared down there, k to the 1.5 upstairs. So they cancel. It becomes like 2 minus 1.5 is 0.5. So we get limits k goes to infinity, ln of k over k to the 0.5 is like k to the 1/2 square root of k. Okay, so we know ln of k actually grows slower than all the power functions. That's not only polynomial, so any power function, it could be square roots, it could be cube roots. So here the denominator is bigger, so we get this guy is 0. This guy is 0. It means what happened? It means the denominator is a big guy and the numerator is the small guy. So now let's look at our P series. So by the P test, our P series was P series. So k from 1 to infinity. 1 over k to the 1.5. We know this guy, as long as the P is greater than 1, we have convergence. Okay, then by the limit comparison test, see, now the big guy converges. What can you tell about the small guy? The small guy also converges, so that's why our series a sub k also converges. Yay, we figured that out. So this problem is actually quite interesting. And this is what happened to math, right? Some problems, you try one way, doesn't work. You try another way, doesn't work. You just keep trying. So I hope this problem can open your mind. Okay, but don't worry, your exam problem, you won't have like this kind. This problem is to open your mind. All right. So that is it for sessions 8.5.